The U.S. Geological Survey, we were talking about what it first came in at, has reduced the number to 6.6. I'm going to bring in now a professor and expert on this. Dan Springer, stand by. We will come back to you as the news warrants. John Rundle, professor of physics and geology at the University of California, Davis, and director at the California Institute for Hazard Research of the University of California, joins me now by phone. Mr. Rundle, 6.6, what does that mean?
That's a pretty violent earthquake. The source dimension for that is probably on the order of something like 30, 40 kilometers, so about the same distance as it was deep. It was about 40 kilometers deep. And as you said earlier, it was pretty much right under Anchorage. The problem that one is going to see in Anchorage is similar to the Good Friday earthquake of 1964. The ground in that area, a lot of permafrost, very loose, very able to flow. There's a problem with liquefaction, and what that means is under violent shaking, the ground basically turns into a liquid and kind of flows. And essentially what you're seeing there in the street is that the effect of that. The roads are buckled and cracked, and it destroys foundations. If you remember the Christchurch earthquake, the magnitude 6.1, I think, earthquake in Christchurch in February 2011, that basically destroyed the city of Christchurch because it occurred right under the city, and much of the ground liquefied. There was much liquefaction going on there.
That's very interesting. I lived, and you mentioned the word permafrost. I lived up in Minnesota, and whenever we would go north, we would see areas that never thawed. Is that what you mean by that, perma?
Yes, and unfortunately, because of global warming, the permafrost is starting to thaw. And in fact, not only do you get situations like this, but you're also getting a lot of methane produced. And that's, methane is a much more active global warming gas than carbon dioxide. It's about a factor of 4 or worse. So there's lots of problems associated with the thawing of permafrost.
You're talking about melting that has occurred. I have I've got an update here, and I'm glad you're on the phone with me. The Associated Press now has revised what it was being told and is now reporting a 7.0 earthquake.
Okay, so that's not too surprising. The initial reports are often low, and they go up with time.
Is that a much bigger, I mean, does 6.6 to 7.0, is that much of a jump in terms of damage or injuries that we might see?
That's a fairly large jump, so to speak. Essentially, you can expect something like a factor of, I'm going to just say offhand, a factor of 7 to 8 higher in energy release. In seismic wave amplitudes and so forth. So that's actually significant.
All right. So we do have some pictures that we've been showing people as they were in their office buildings in Anchorage. I mentioned that the epicenter was estimated 7 miles away, but what Professor Rundle is saying is that's almost underneath the city because of the permafrost situation, that liquefaction that goes on underneath the ground in that part of the world. So as we go back to those pictures, notice how how they're reacting to this. This went on, according to what we can see, for a little bit, long enough for people to register, oh my goodness, and then find a place to jump under. That often speaks, and I lived in Northern California when the big one hit, the Nimitz Freeway, so on and so forth, and I remember the time and how long people had to move around and get under things. And sometimes that can create difficulties. You saw the one person on the stairs there. Professor, your thoughts?
So basically, when an earthquake is that close, there are two kinds of waves, a primary wave and a secondary wave. The primary wave often doesn't do the damage. It's really the secondary wave. And when it's that close, the difference between the two, as in Alaska, the difference in time between the two is only a second or two, whereas in California and Loma Prieta, if you were in Oakland, you probably had something like 10 seconds to react to it. So when the first shaking starts, a lot of times seismologists start counting in seconds, and they can basically tell from that how, when the violent shaking starts, how far away the earthquake was. It's a topic called dispersion, basically, dispersion of seismic waves.
We are going to continue to cover this. I know you mentioned some weather elements there, and there's a lot of disagreement on how we get to different places scientifically, but I want to make it very clear, an earthquake is not meteorological, it's geological, and what you're saying is that sometimes things like water can have an effect in an earthquake because of where this is located. Professor Wendell, thank you.